Hello, students. So sorry that today we're not able to meet in person because of the weather. I hope you're staying warm and safe at home. All right, so what we're going to do is we're going to go ahead and proceed with the lecture we're going to have today. You'll be able to follow along in your book. I believe I might have a page number on there for you. We'll see. And what we'll do next week when we get together is that I will, proceed to the next lecture, but I will bring the stuff for doing the lab we were going to do today. Okay, so I'll tell you what we're going to do, and then we won't miss anything is what I'm trying to tell you. We'll be fine on all our stuff. Okay, so let's start here with, we're talking about motion, and this is a picture of a famous Christian theologian, a guy who studied a lot. His name is St. Thomas Aquinas, and he wrote some pretty important Christian literature. And he came up with the idea. He said, look, I have 5 proofs for the existence of God. And we can see his list over here: motion, cause, possibility and necessity, perfection, intelligence. All of these things, they get rather philosophical. But we're going to look at right here that very first thing he said: motion. Okay, so motion is, according to Aquinas, proof of God's existence. That's pretty cool. Someday you may study Aquinas in a literary class or a Bible study class, something like that. Okay, so what is a force? We're going to start with this. A force is a push or a pull on something. Pushing and pulling can move objects. So right here we're seeing a force and we're seeing something move. So we're finding motion, right? So a push moves it away from you, a pull moves it close to you. So therefore, in order for something to move, it has to be acted upon by a force, and that we can see that happening, or it's actually moving. All right, so a force is needed to make an object go faster, slow down, or change direction. All that would be considered movement. We have a guy here hitting a golf ball, and it's moving and falling down into the hole right there. Pretty cool. Okay, so forces, when something's moving, you may have noticed if you throw a ball or kick a ball or something like that, eventually it stops, right? So there are other forces that oppose motion. And the main ones we'll be talking about are friction and gravity. All right, so if we start to kick a ball across grass, for instance, eventually it will stop rolling, and it has to do with the action that it is as it's rolling on the grass. The grass has a lot of friction, and it's kind of rough. You can see down here at the bottom. It's going to stop the ball rolling faster than here. If you ever slid something across a slick floor, or even go sliding yourself in your socks, and you slide across a slick floor, and it's kind of fun that you go sliding past. Well, you can't do that on a carpeted room, right? Because you will stop. Your socks will stop you. That's because there's more friction between your feet and the carpet than there are between your feet and a slick floor. But the other thing is that everything's being pulled by gravity. So there's a lot of philosophical, scientific talk about gravity. Is it really a force? Is it actually just the result of the Earth spinning and moving through space? We don't have to get into all that. So just for simplification purposes, we're gonna call gravity a force, even though technically it's really just a response of the way it's acting. All right, so we can see a picture down here of the Earth and the Moon. What we do know is the Moon stays in orbit around the Earth, right? And the thing that's keeping it in orbit is the gravitational pull of the Earth. Also, the Earth is in orbit around the Sun. What's keeping it in orbit is the gravitational pull of the Sun. So things that have large amount of mass will have a large amount of gravity. Okay, so if it's big, it'll pull harder on something. So the Moon, therefore, has less gravity than the Earth because the Moon is smaller than the Earth. You personally, because you have mass, you have gravity. Okay, so it's just so negligible, that means very, very small, that you can't really notice it. Okay, so but it does fall into the idea of motion. If you think about it, if I drop a ball, what's it going to do? It's going to fall down. What's going to be pulling it down? Gravity will be pulling it down. Okay, so in this case we're saying the force of gravity will pull it to the ground. If I drop the ball 100 times, how many times will it hit the ground? Yeah, 100 times, right? So gravity is a pretty fairly well established scientific principle. In fact, it's called the law of gravity because it does the same thing every single time. And so gravity is conforming to certain laws of nature, okay? And those laws have to do with these things we call forces. There are some things called invisible forces, gravity being one of those. We can't actually see it, but we can see what it does. So let's see. We're going to throw a baseball straight up into the air. Eventually, it's going to come down. If you throw it up, you've probably done that, where you throw a ball to yourself, right? You throw it in the air and you catch it. You throw it up and you catch it. The force pulling it down is called gravity. And when you weigh yourself on a scale, it's measuring the force which gravity exerts on you. So when you stand on a scale and weigh yourself, that reading that you get on the scale is based on being on the earth, because the earth pulls at a certain amount of force, 32 feet per second squared. It's pulling down on you at all times. And remember, it has to do with the mass of the earth, not the mass of you, the mass of the earth. And so therefore you can see that you're going to weigh a certain amount based on where you are. And since in this class we're never going to leave the planet Earth, then we will be looking at that weight and mass on the earth are going to be the same thing. Now notice in this picture over here, we're going to see a ball being thrown up in the air. It's going up and it's coming down. You know the old adage, what goes up must come down. I want you to notice when it gets right to about here, probably about right here, not shown, for that split second, that little tiny moment, an instantaneous piece of time, that ball is actually weightless, right? It has nothing acting on it. It's not being pulled, it's not being pushed, it is just weightless in the sky. So that's kind of cool right there. It doesn't have any gravity at that moment right there. Okay, but it is going to return to the surface of the earth, obviously. All right, I think we're going to watch a little video here. Oh, I love this one.
Suppose you wanted to move a small rock. You couldn't do it just by wishing the rock would move. And you couldn't do it by magic. And you couldn't do it by ordering the rock to move. There's only one way you could make the rock move, and that's by making a force act on it. What's a force? That's something that pushes or pulls something else, like the force from a hand pushing the rock or pulling it. It doesn't matter what does the pushing or pulling. As long as it applies a large enough force, it can move the rock. In fact, the rock can even be moved by a force that you can't see, if you do this, for instance. When you do that, the force moving the rock is called gravity. Gravity is a force pulling the rock toward the center of the earth. Gravity pulls everything else in the world toward the center of the earth also, including you. Gravity was pulling on the rock all along, of course, but when the table was there, that kept the rock from moving down. If you remove the table, you allow the force of gravity to move the rock. And when you pick the rock up again, you use another force, this time to lift it. So whenever you make this rock move, you do it by making a force act on it. In fact, anytime anything at all that's not moving starts moving, it's because some force acts on it.
Okay, you gotta love the caveman, huh? Okay, and this next one is another one of my favorites. If you've ever had a science class with me before, you've seen it. But it's Schoolhouse Rock, and it's just classic.
Gravity, help and wash the dishes, and I drop a cup. Why does everything fall down instead of a cup? Riding up the hill I spill and hit the ground. Wish I could fall up instead of always falling down. Down, 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 down. I'm a victim of gravity. Everything keeps falling down on me. No matter where I go, the force is there, I know. Down, 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 down. It's all around town now. It's like a magnet deep inside the ground. When I lift something up, I feel it pulling down. Pulls me in the pool, pulls rain down on me. I'm a victim of down, 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 gravity. seems right. It is love that makes the world go round, you see. Power of gravity. But please, don't tell Mary Jean. Now. Without Earth's gravity to keep us in our place, we'd have no weight at all. I'll be in outer space. The sea would float away, and so would fields and towns. Down, 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 down. Yeah. Isaac Newton underneath the apple tree. One hit him on the head, he said that must be gravity. Newton's law of gravity says that every object in the universe pulls on every other object. The bigger the object, the stronger the pull. But the greater the distance between the objects, the weaker the pull become. Come back, Mary Jean. Don't call me clumsy, don't call me a fool. When things fall down on me, I'm following the rule. The rule that says that what goes up comes down like me. I love it. Down, 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 gravity. Shoo-be-doo, down, down, down.
Okay, there you go. That's a classic, y'all, talking about gravity. Okay, so when we are talking about gravity being this force that's pulling us down, that's how we measure weight. I discussed that earlier, right? It's the measure of the pull of gravity it has on us. Now, the mass is how much matter is in an object. So for us, because we're on the Earth, weight and mass are going to be the same thing, but they are different. Okay, so mass doesn't change if you go to the moon, but your weight will, because the moon has less gravity than the Earth, right? So if we took a scale on the Earth, and we're going to look right here at a person who is on the Earth, and they're going to weigh 140 pounds on the Earth, that same person is going to go to the moon on the same scale, and the scale here, his shape didn't change at all. The man's shape doesn't change at all. But he's only going to weigh 23 pounds on the moon. Why? Because the moon is pulling less. This arrow shows how much the pull is. So the Earth's pull is this much. The moon's pull is only this much. Now Jupiter is our largest planet, and look at the pull. It's very strong. And if you could stand on Jupiter, which you can't, this same person would weigh 355 pounds. Now, the sun is massive, very big, has a very strong gravitational pull. It's keeping all the planets, orbiting around it. And if you were able to stand on the sun, you would weigh 3,914 pounds. This man would. So, wow, that's a big difference. So you just need to know that the weight has something to do with where you are. The mass is how much space you occupy, right? And so, therefore, the mass doesn't change, but the weight does depending on where you are. All right, other forces at work on moving things. An object will stop moving by itself if you push it or whatever, and it's due to the invisible force called friction. Like I said, when you're sliding across the floor, right? So in this particular case, we have a box on another box, I guess, and we're pushing the box across here. Notice the arrow of the force is going this way, the motion is going this way, but the friction is acting opposite to that, okay? So when it's acting opposite, eventually it's going to oppose it so much that it'll stop it. Okay, so in my physical science class, we have to actually do mathematical problems about the way the static force and the dynamic force and things like that are affecting something that's moving or about to move. And so fortunately for this class, we don't have to apply any math equations to it. Another invisible force, which is a ton of fun, is called magnetism. So think about it. I'll show you a picture in just a minute. If you play around with some magnets, you can cause some things to move, can't you? In fact, one of the things I'll do for our lab is to bring you some magnet stuff to kind of do some experimentation with. A magnet doesn't have to touch an object to put a force on it, which is kind of cool because it's got that field, this called a magnetic field around it, and the field can manipulate things and move them. A magnet can pull on objects that are magnetic, usually metals. And magnets are found naturally. They're in a mineral called magnetite. They were originally discovered in a Greek island called Magnesia, and that's why they have the name magnet, actually. Other magnets we can make. In fact, most of the magnets we use in science class have been made in a factory. You know how they, I don't know, the way they make them actually is to take a piece of metal that has the capability of being a magnet and running a bunch of electricity through them. And it's like electromagnetism. It turns out electricity and magnetism are very much related to one another. So if I run a lot of electricity through a piece of metal, I can actually turn it into a magnet. Now this is a fun picture. Watch this. Okay, so I wanted to show you here. Look, definitely we have motion. What I have on the left are some of those little tiny ball magnets. And on the right is a very, very strong called neodymium magnet right there that pulls it and moves it just like that. So that's a lot of fun to move things around with magnets. All right, let's watch a little thing. Now, I will tell you, the force itself, you know, how things are moving is still a little bit of a mystery, even to the smartest scientists in the world. And so we're still trying to figure out some of that. We have some ideas. Let's watch this video to give us a little better idea.
If you've ever played with magnets, you'll probably notice that when like poles of the magnets are facing each other, so two norths or two souths, the magnets will repel, but hold two unlike poles together, they will attract. Magic. Well, not really. And here's why. All magnets have something called a magnetic field. Magnetic fields are invisible and surround the magnet, causing a magnetic force. This is what causes magnet materials and magnets to either attract or repel. Magnetic fields always follow a few basic rules. Even though magnetic field lines all have the same strength, the strength of the magnetic field is greater the nearer to the magnet. Can you guess why this is? It's because the field lines are more concentrated, increasing the overall strength of the magnetic field. If you think of a magnet, you don't see lines coming out of the poles. Magnetic field lines are invisible, but there are two things we can do to show the field lines. Iron filings can show us the shape of the magnetic field, which we show as a simplified diagram like this. So iron filings show us the pattern, but they don't show us the direction, which is where compasses become useful. So how can compasses show us the direction? Place some small compasses around a magnet. The arrows of the compass will move so that they are pointing towards the direction of the magnetic field. Then, using a pencil, draw a dot where each arrow points and then connect the dots. The compasses will show the direction of the field lines going from the North Pole to the South Pole. Simple. We now know the direction of the magnetic fields. We will look at compasses and the Earth in another video. There are two different types of magnets, permanent and induced. Permanent magnets are always magnetic, meaning that their magnetism can't be turned off. Whereas induced magnets aren't always magnets, they are unmagnetized most of the time. But when placed inside another magnet's magnetic field, it acts like a magnet and attracts. Magnetic materials like iron and steel can be turned into magnets. If you place an iron paperclip close to a permanent magnet, but without touching, the paperclip will become an induced magnet, with the end nearest the magnet having the opposite polarity of that of the magnet. Because the paperclip is now an induced magnet, we can add another paperclip to it, and another paperclip. This is of course a temporary process. Remove the nail of the magnet and the nail will lose its magnetism. So in this video, you learned about the north and south poles in magnets, attraction and repulsion of magnets, magnetic fields, and the difference between permanent and induced magnets.
All right, you see there's some, that's really a description of what they're doing, but we really don't know how. That's called the mechanism. We're not real sure about it. But we do know some things. We know that they each have two poles, a south pole and a north pole. You've probably heard of a south pole and a north pole, and what do you think about when you hear about a south pole and a north pole? Probably the Earth, right? Well, it turns out the Earth is a giant magnet. There's a giant magnetic field going around it. That's why one of the reasons we believe that in the middle of the Earth it's probably some sort of metal because of the magnetic attraction we have on the Earth. It turns out that the magnetic field does help us. It shields us from some of the damaging rays from the sun, which is very nice. It's almost like a little force field around us. So if I have this kind of magnet, it's called a U-shaped magnet, right? I have the north and the south pole like that. These are typically fairly weak. You've seen probably some with a hole in the middle. We can use those. I'll have some of those to show you. One side, the top side, would be the North Pole, and in this case, the bottom side would be the South Pole. Oftentimes, we'll have a bar magnet like this, and the bar magnet actually usually tells you which side is south and which side is north. And then you can take it to move things around. Now, in the video when it showed the paper clip becoming magnetic, you can try to see how many paper clips you can hang from it, and then you know, you can't hang a ton because the paper clip will become less and less magnetic. But there can be a moment in time where you take the original paper clip off of the magnet, and it will still hold on to the other paper clips briefly because it will maintain some of its magnetic pull on it, which is pretty fun. All right, so lab time. What we would have done during lab time would be to do a kind of a friction experiment. I have this board that we can push up and something would slide down it, and we would make predictions about how fast and how quickly, at what angle some things would slide down. That I would have you predict, you know, if like something that's rough like a eraser or something might go slower than something that's slick. And then of course we could put something with wheels on it, right? The wheels are definitely going to reduce the friction by giving the ability to roll, right? That's what we call a simple machine, is what we're going to talk about next week. All right, here we go, some magnet fun. We would take a magnet and see how we can make it move. So that's what we're going to do, and like I said, I will go ahead and bring that next time. I think we are talking about, is it simple machines next time, I think? And so this would play into that just fine, that we can still have some magnet fun. Oh, this was another video, but I don't think we're going to watch that today. Okay. Oops, it's going to play it. Yeah, that's for my older students. Okay, y'all. Well, I hope you enjoyed this and that it has informed you somewhat. We will get together next week and make up for all this. Once again, I apologize that we're not together. I miss seeing y'all, and I hope everybody's safe and warm and everything, and I will see you next week.